Hey everyone, just wanted to republish and sort of revise the infinite product I did my last video. I know it's been a whole month since then, but I've been busy with school, so I apologize for the gratuitous uploads or lack thereof. However, well, let's get into it. First off, we're going to let this product equal to p. And then we're going to try and find the general term of the product. So the general term would be, so it's going to be as k equals 0 to infinity, the product. And now it's going to be the 4th root of 2 times the 16th root of 4. Okay, so it's squares. But we're starting out at 0, and we're starting at 2, right? So it's going to be 1, no. Sorry. It's going to be 2k plus 2 to the 1 over 2k plus 2 squared. All right. Now the denominator is going to be 2k plus 1, so it's going to be odd, and then to the 1 over 2k plus 1 squared. Alright, there. So now that we have the general term, we can take the log of p, and then take the log of the product form. So we get the log of p equals the following infinite series. It's k equals 0 to infinity. Okay, as you know, the log of any product equals the sum. It's just, yeah, okay there. So the log of any product equals the sum of the log of each individual value that is being multiplied. That makes sense. Just simple product rule. And now, so if we apply this to an infinite series or an infinite product, then we get like an infinite sum, which is quite nice because you can work with infinite series a lot easier. It's like a hypergeometric series and like dialogues and not dialogues. Well, yeah, dialogues and digammas. So you have a much greater repertoire with series or with sums rather. Okay, so it's just going to equal this. Now you take the log. It's going to be a log of 2k plus 1 divided by 2k plus 1 squared. There. Okay, now we have that. Okay, these series are fairly challenging, actually. But believe it or not, the sum of a bunch of logarithms, it's going to be challenging. But here's a method that I've devised. It's sort of like a Feynman technique, but it's applied to sums. So it's a little bit strange. But so we're going to let this new function, f of x, equal to, terrible equal sign, equal to the sum, so k equals 0 to infinity. We're going to have 1 over 2k plus 1 to the 2 minus x, minus 1 over, 2k plus 2. 2k plus 1 to the 2 minus x. Okay, so I did this transformation because f prime of 0 actually equals log of p. Alright? And here's a way to prove it. So x to the s minus 1, or any logarithm log of anything, log of a, we'll say, is equal to the derivative d over ds, I'll say, d over ds for a to the s. But then we're going to let s go to 0, right? Where we're valuing s equals 0 at the end, after the differentiation. So we're doing that, but we're going to let our constant equal 0, x, in this case, equal 0 in the future. We're going to like factor out the derivative in a sense, I guess. Might be a way to put it. Anyway. Oops. So now that we have this, Jesus Christ. Oh my God. What happened? Jeez. Okay. Sorry about that. My Microsoft whiteboard nearly just crashed on me. That's fine. Okay, so now to evaluate these two series, we're going to, for the first one, we're going to factor out a 2 from the denominator, so that's going to be equal to the sum, or here, going to be equal to 2 to the 2 minus x, or 1 over 2 to the 2 minus x, so it's going to be 2 to the x minus 2. 2 to the x minus 2 times the sum. K equals 0 to infinity for 1 over 2k, or no, 1 over k plus 1 to the 2 minus x. And so this is going to be equal to 2 to the x minus 2 times Riemann zeta of 2 minus x. Okay, so that's the first series down. Now the second one is not nearly as trivial, but still pretty easy. I don't know why I erased that. Undo that. Okay, now the second series, to evaluate this is going to be the series. This k equals 0 to infinity, 1 over 2k plus 1 to the 2 minus x. Okay. And now we're going to, once again, factor out a 2 from the denominator, and then we get 2 to the x minus 2 times the sum. K equals 0 to infinity for 1 over k plus 1/2 to the 2 minus x. There. And now this is going to be the Hurwitz zeta function of, is actually equal to 2 to the x minus 2 times the Hurwitz zeta function of 2 minus x and 1/2. I'll put a link in the description below for more on the Hurwitz zeta function, if you're interested. Okay, now there's a cool identity regarding the Hurwitz zeta function of 1/2 as its second input. That's going to be, I'm just going to apply it here real quick. Get 2 to the x, or no, here, I'll put it at the top for now. And you get a Hurwitz zeta function of x and 1/2 equals 2 to the x minus 1 times the Riemann zeta function of x. All right. So we're going to use this identity right now and apply it to a situation here. So then we get 2 to the x minus 2 is going to be 2 to the 2 minus x minus 1 times the Riemann zeta of 2 minus x. And, okay, now distribute the 2 to this and this. And we, sorry about that. And we get, it's going to be equal to 1 minus 2 to the x minus 2 times Riemann zeta of 2 minus x. Okay, there. Now that that's done, we have both of these sums evaluated. The first one equals this, and the second one equals this. So all we have to do is subtract one from the other, and we get log of p, hope you can see this, log of p equals 2 to the x minus 2, it's Riemann zeta, 2 minus x, minus, plus 2 to the x minus 2, times Riemann zeta, 2 minus x. I'm adding because I distributed the negative, by the way. Just throwing it out there. And then subtract, finally, Riemann zeta of 2 minus x. Okay, now this, or no. This is wrong. Sorry. No, this is equal to f of x. So now we have to differentiate both sides of the equation with respect to x. And by doing that, we get, okay, apply the product rule here. Or actually, no, we can combine these two. That's really nice, actually. So then we get 2 to the x minus 1 times Riemann zeta of 2 minus x, and then minus what? Minus Riemann zeta of 2 minus x. So then we can finally factor out 2 to the x minus 1. I forgot this happened. 2 to the x minus 1 minus 1 times Riemann zeta of 2 minus x. Okay, yeah. Now we have to differentiate this function right here with respect to x. It's pretty simple. You're going to get here. Write this out a little bit clearer. F prime of x is going to be equal to log 2 times 2 to the x minus 1 times Riemann zeta of 2 minus x. Oh god, terrible Riemann zeta. Yeah, I'm gonna fix that. Riemann zeta of 2 minus x. There. And then it's going to be differentiate the Riemann zeta, and then so that's going to be minus 2 to the x minus 1 minus 1 and Riemann zeta prime of 2 minus x. Yeah? Just gonna check this. Yep, that makes sense. Okay. So now, remember up here we had a formula. Where's our formula? And, oh, I think I erased it. It doesn't matter. If you remember, f prime of 0 equals the log of the product we're trying to evaluate. So now we just have to let x equal 0 here. So finally, we get f prime of 0 is going to be equal to it's going to be equal to log of 2 times, okay, so that's going to be 2 to the 0 minus 1. It's going to be 1/2. And divide by 1/2, or divide by 2. Then we get Riemann zeta of 2 minus, okay, that's going to be 2 to the 0 minus 1, so that's going to be 1/2, then minus 1, so it's going to be minus 1/2. So then minus minus, you get plus 1/2, Riemann zeta prime of 2. Okay. So I think that's right. Yep. Seems to be right. And so now, Riemann zeta of 2 is famously equal to, you're just going to write that down, log 2 divided by 2. Riemann zeta of 2 is famously equal to pi squared over 6. Then you get pi squared over 6, and then once again divide by 2, and you get pi squared over 12. So then add pi squared. Okay, so Riemann zeta prime of 2. Now this was found by Glaisher, not Euler. Equals pi squared over 6 times log of 2 pi e to the gamma divided by a to the 12, where a denotes the Glaisher Kinkelin constant. And so I think I did this right. Yeah, okay. So then pi squared over 6. So finally, you can combine these two together. Here, let me simplify a bit. 1/2, 1/6. Did this earlier. 1/12. Now we can factor out a pi squared over 12 and then add the logarithms. So then we get log of p is equal to, okay, so it's going to be pi squared over 12 times log of 2 plus log of a bunch of random cool constants and shit. So add these together, and we get log of p is equal to pi squared over 12 times log of 4 pi e to the gamma over a to the 12. And so now, due to the what was it, exponential rule of a logarithm? Is that what you call it? You just put the factor of the log into the exponent of the argument. So then you get log of p equals pi, or no. Sorry about that. Equals the log of 4 pi e to, oh, screwed that up. God. Okay, 4 pi e to the gamma divided by a to the 12 quantity to the pi squared over 12. So raise both e to both sides. Take the exponential function of both sides of the equation. And finally, you get p, the product that we desire, is equal to 4 pi e to the gamma divided by a to the 12 all to the pi squared over 12. Okay, that's it. Yeah, there's nothing more to elaborate on. So, see you later. Thanks for watching.